Welcome back to Dissect the Question. A police trainee presents to the police academy clinic complaining of cramping of the fingers on his right shooting hand during practice sessions on the shooting range. He reports that his father is a retired police officer who suffers from leg cramps. The examining physician states that an inherited mutation of the SERCA pump and or a calcium channelopathy could be responsible for such cramping. Which of the following best describes normal regulation for the skeletal muscle sarcoplasmic reticulum calcium, SERCA ATPase, and the physiological state of the ryanodine receptor calcium release channel? Well, this sounds a little complicated. We could theoretically answer it without the vignette, but let's dissect it by looking at the vignette and looking for the clues. That'll give us more surety that we're answering it correctly. So we have cramping, and the cramping seems to be genetic because his father has leg cramps. So it makes sense that a mutation that's inherited of some muscle, okay, protein, the muscle protein, is presumed or suspected to be SERCA, or some channelopathy, that means a pathological function of a calcium channel, could be responsible for such cramping. So, let's see the interaction. Based on this question, we're talking about the sarcoplasmic reticulum, a calcium pump, ATPase, which is an active transport mechanism for getting calcium out of the sarcoplasm and back into the sarcoplasmic reticulum, and the ryanodine release channel. So this question is giving us all the information we need. We just have to use our logic and our knowledge to what? Piece it all together. So let's look at the sarcomere. We should draw a simple cartoon of what we know about a sarcomere. So a sarcomere is the space between two Z lines. Attached to the Z lines are thin actin filaments. And between the actin filaments, we have a thick filament known as myosin. And we know it's the cross-bridging that occurs between the actin and myosin filaments that produces active tension for purposeful movement. Now, even though we need active tension for purposeful movement to occur, we need contraction plus relaxation. And in a muscle spasm, we only have contraction. That's the definition of a spasm. The muscle contracts and has difficulty relaxing. So let's see how this plays out. Contraction plus relaxation. We don't have relaxation in a muscle spasm, which means that the cross bridges would get stuck and they would never go back to their original conformation. Now, to make those cross bridges, we know we need calcium to come in through the T-tubules associated with the SR, the sarcoplasmic reticulum. And to get calcium out for relaxation, here's the calcium going out, we have a SERCA, a sarcoplasmic reticulum calcium pump, an ATPase for actively transporting the calcium out against its concentration gradient. So, the question is asking, is the calcium ATPase activity only high when the calcium channel is closed? Is it low when the channel is closed? Is it low when the calcium channel is open? Or is it the same when the calcium channel is closed and open? This would be very difficult to figure out if you didn't really know the concept and didn't know how this mechanism works. So since we're dealing with circa and cramping, we have to think about what's going to cause a contraction without a relaxation. Well, one way is to what? Block the circa pump. Okay? So there's nothing here that suggests that the circa pump, the calcium ATPase, that's the circa pump. The calcium ATPase is the circa pump. Nothing here to suggest that we're blocking it at any time. Question is, how does the calcium ATPase work in relation to this ryanodine receptor? It's called the ryanodine receptor calcium release channel. In other words, how does the skeletal muscle normally relax? Well, it turns out that contraction is a result of depolarization of the T-tubules. Of course, first we have to have depolarization of the sarcolemma, that is the plasma membrane. Then it gets transferred to the T-tubules, and that releases the sarcoplasmic calcium through the ryanodine release channel. Ryanodine release channel is just a plain old voltage-gated calcium channel. So if we had a channelopathy, here we have channelopathy. If we had a channelopathy, it would mean that if that calcium release channel got stuck, we'd have so much calcium coming in, it couldn't be pumped out fast enough, and that could produce a muscle spasm. But that would be a mutation of the ryanodine receptor calcium release channel known as a channelopathy. We're not asking about that. Only we're asking about what's the relationship between the circa pump and that channel. It turns out that the calcium ATPase activity is always going on. Now, this is a good lesson in biology. In all cells, calcium is an important signaling molecule. And through evolution, all of our cells have calcium exchangers or calcium pumps that constantly want to remove the calcium. Imagine if we had calcium accumulating in cells, new calcium coming in would not be easily recognized. But if calcium level is low inside cells, then new calcium coming in for signaling is going to be detected very easily. So there are many mechanisms to constantly removing calcium, and circa is one of them. So it turns out that circa pump is always active, whether the calcium channel is open and closed. Now, you ask, how then do we get relaxation? Well, when the motor neuron stops firing and less acetylcholine is released, the acetylcholine that stops being released doesn't cause depolarizations. So when the depolarizations go away, that's when the circa pump becomes more effective. Even though it's always acting, it's not effective during depolarization. It's only effective when the depolarization stops. So relaxation is really initiated from the motor nerve that stops depolarizing the sarcolemma and T-tubules, and therefore stops the calcium release, so that now the circa pump can be more effective at removing the calcium and causing the relaxation.